Hardware specs are only a fraction of the story if your PID loops are poorly tuned. Mastering PID tuning is essential to unlock the true potential of these proprioceptive actuators. Many developers struggle with actuators feeling too soft in position mode or violently vibrating under load. Usually, the issue isn't a hardware limitation, it's tuning the loops in the wrong order. To fix this, we need to understand Baer's internal control hierarchy. It is a pyramid structure where higher level modes rely on the stability of the lower level loops. Today, we're going to walk through how to configure and tune all 4 operating modes step by step. Let's start with an absolute rule. Every high-level mode, whether it is velocity, position, or direct force, ultimately feeds its output into the lowest layer, the current loop, specifically the IQ and ID loops. In proprioceptive motors, output current is directly proportional to output torque. If your current loop is unstable, any control algorithm you stack on top of it may fail. Fortunately, you rarely need to tune this from scratch. The factory default current loop parameters are already optimized for the physical characteristics of each series, as this spec sheet shows. For this demo, we are using the Koala Baer with the default current loop P and I gains. In mode 0, or torque mode, you command the goal IQ directly. Under normal operation, your IQ and ID/PID parameters must be identical. Here is your first critical pitfall warning. The current loop D gain must always remain at 0. A stable current loop is the foundation of everything else. Once your current loop is rock solid, we can move up to mode 1, velocity mode. Here, the velocity loop output feeds directly into the current loop, meaning you have 2 loops running concurrently. For velocity mode, the baseline parameters setting velocity P between 0.5 and 1, I to 0, and D to 0 are initial testing benchmarks to ensure safe power-up. In real-world engineering setups, you must dynamically adjust these gains by monitoring whether the present velocity is actively catching up with the goal velocity on your oscilloscope. In the velocity tracking plot, you can observe that the initial tracking performance is relatively poor. As we gradually increase the velocity loop P gain, the tracking accuracy improves significantly. If a steady-state tracking error persists at peak velocities due to internal gear friction, introduce a tiny fraction of I gain, typically between 0 and 0.01, to eliminate the residual offset. Next up is the core focus, Mode 2, Position Mode. This operation engages a classic 3-loop cascade architecture nested as position over velocity over current. The tuning metric for this layer is straightforward. The present position should closely trace the goal position with a fast rise time while minimizing transient overshoot as much as your mechanical system allows. A practical workflow for position tuning. Step 1. Establishing the baseline. Start with your pre-tuned velocity loop parameters. Initialize your outer position P gains at a low baseline value. Ensure the position integral I and derivative D gains are kept 0 to prevent low frequency windup or sluggishness when approaching the target coordinate. Step 2. Boosting rise, time, and stiffness. Gradually scale up your position P gain. As it increases, you will feel the static holding stiffness of the joint multiply, and the tracking response toward the target coordinate will significantly accelerate. Step 3. Balancing, damping, and eliminating overshoot. If an overshoot occurs, you can suppress it by either increasing the underlying velocity P gain or directly adding position D gain for convenience. Since position differentiated over time is mathematically velocity, these two approaches achieve the same fundamental damping effect. Finally, if your tracking gains feel dialed in but the joint still yields or sags under heavy external or gravitational loading, the issue likely isn't your loop tuning. It is often that your limit I max register is set too conservatively, bottlenecking the maximum output torque capability of the underlying FOC coils. In summary, avoid treating cascade tuning as a rigid, unyielding formula. Whether you choose to lock position D and rely on velocity P for damping, or prefer the convenience of dual loop position PD coordination over a stable velocity baseline, the goal remains identical: a responsive, crisp joint trajectory that matches your specific robotic application. Direct force mode bypasses traditional cascade loops to run an independent direct force loop. It allows Bear to simultaneously track multi-dimensional trajectories containing position, velocity, and IQ data. Goal position defines the equilibrium point for the virtual spring system. The direct force P gain acts on the resulting angular position error. Goal velocity functions as the target velocity for the virtual damper. This is blended into the control loop via the direct force D gain. Goal torque acts as a feed-forward command that integrates directly with the underlying current loop PID gains. Tuning workflow. Step 1. Set the baseline D. The loop simulates a physical spring damper system. Your direct force P gain dictates spring stiffness, and the direct force D gain dictates damping. Start with D set to 10% of P. Step 2. Avoid the I gain. Keep the integral, I gain, at 0. Any I gain will accumulate error, destroy the predictable spring physics, and cause oscillations or violent bouncing upon environmental impact. To wrap it all up, remember the core Bear tuning summary. 1. Trust the default current loop and never touch the D gain. 2. Build cascaded loops sequentially. If the bottom layer isn't stable, the top layer may collapse. 3. For direct force mode, start the D to P ratio at 1 to 10 and avoid using any integral gain. Follow this workflow and your actuators will deliver incredible responsiveness and smooth force interaction. If this breakdown helped your robotics project, hit like and subscribe for more hardware tutorials. Leave your questions or error code issues in the comments below. Get your parameters locked in and let's get those robots moving. See you in the next video.